NASA Kepler Space Telescope mission, and he's here to tell us the recent news on exosolar planets. Thank you. Please welcome.
Press the button and it works. Okay, great. Thank you.
So here's the mic right here. So if you can get closer, you want to pull it closer to you, you can. Okay.
Is that better? Yes. Good. Okay. Well, Bob talked about being focused, and I'll be telling you about a mission, the Kepler mission, that was very focused. One instrument, one task, and it has been so far very successful. Basically, its job is to find the frequency of planets, Earth-sized planets, in and near the habitable zone of a wide range of stars, but particularly stars like that of the Sun. And so I'd like to show you what we've accomplished so far. When you're focused, you have a set of critical questions that you must answer, and these are the questions that the mission addresses. What's the frequency of Earth-sized planets in and near the habitable zone of stars like our own? What is the distribution of these planet sizes? How many are like Mercury or Mars or Earth? Are there planets that are rocky that are twice the size of the Earth? We know that most of the stars in the sky are actually parts of multiple star systems. So if we want to understand planets around other stars, we ought to ask ourselves about planets around multiple star systems. We also see a lot of giant planets. Something over 460 have been discovered so far, and so we'd like to understand them. The importance may not be so obvious right away, but when you recognize that the belief is that to form these giant planets, you form them out where Jupiter's at, where there was a lot of material to build planets. And these planets came spiraling in and destroyed everything in their path, like Earth-like planets. You recognize you want to understand these objects and how they were formed and how they migrated and what the implications are when you find them. We'd like to understand how what we find is associated with star types. Stars are very much like people. There's a huge variety of sizes and shapes and ages and actually compositions. So we'd like to understand how these planets are associated with different kinds of stars. So when you look into the galaxy and you say, there are lots of G dwarfs, there are lots of M dwarfs, what do we expect to find out there? So that's the questions that are being addressed. Kepler has three different aspects to it, one of which, of course, is to address the mission goals. There's an astroseismic science consortium with over 300 members, mostly in Europe. They basically are trying to understand the sizes and ages of the stars, the structures. The size of the stars are critically important to us. If you don't know the size of the star and you see a transit, you need the size of the star to get the size of the planet. And you need it to very high precision. You'd like it to 10%, 5%. Generally, people know the size of a star often to within a factor of 2. If they're good at it, to 25%. So you really need to understand the sizes. You also would like to understand the ages of these stars, because the ages of the stars are coincident with the ages of the planets. Young stars, young planets, young planetary systems. There's a guest observer program that basically allows people who are in the science community to go out and, when we look at all these stars, to try to understand the astrophysics that's out there, the strange things that are out there. And I'll show a little bit of that as well. What's the instrument like? The instrument basically is a Schmidt-type telescope. Many of you are familiar with those. Some of you have things that are rather similar that you use for your own observing. It is different than Schmidt-Cassegrain. But basically, it's a photometer. It's a telescope with the CCDs at the focal plane, and this allows you to monitor a huge number of stars, over 150,000 stars, We have a 1 meter aperture to get enough photons. We're looking for transits. A transit means a planet-like object, an object moved across the star, blocked some light from that star. The amount that it blocked tells you the size of the star, the size of the planet, and the orbital period is telling you, is that planet close to the star, in which case it's very, very hot? Is it very far away, in which case the atmosphere is frozen out, or water is frozen out? Or is it in the Goldilocks zone, the zone where you might have liquid water, you might have an area conducive to life? You need to see like 3 transits as a minimum. One transit is like a spot going across a star. Stars have spots. Spots are as big as the planets we're looking for. So if you see something that's very, very irregular, that's not a spot on a star. They come and go as they please. It's an orbiting object. And so you need to see at least transits. And the more transits you see, the higher the signal comes out of the noise, the easier to see it. Now, if this task were easy to do, it would have been done. It's not easy to do. The signals that we look for are buried in the noise. And people say, why don't you really solve the data? Well, they're just bunches of zeros and ones. If we showed you what the signals look like, you would say that's crap. There's no signal there. There is a signal there. You just need to dig it out. And so you need several transits to say, I've got a planet. I don't have a spot, a noise, a fluctuation in my data. So we need to observe, if we're trying to find planets in the habitable zone, 3 years, 3 transits, or 4. 4 are much better. So the orbit has the spacecraft has to live for several years, operate, get this data for you. It has to look at a single area of the sky so it can see these transits. Transits are the order of hours long. Orbital periods in the habitable zone are months and years. So don't blink. This should be, when it's designed properly, the most boring mission ever designed. Okay? And unfortunately, it has entertained us occasionally. And it's gotten itself into trouble. And it calls home and tells us we need to go and help it. The system can look at 170,000 stars simultaneously, watch for transits around any of those. It has a 30-minute cadence. That is to say, it integrates the data for 30 minutes and then stores that, sends it to the Earth once a month. It can also operate on some 500 stars at a 1-minute cadence, which means you can watch the planet cross the limb of a star, which takes the order of minutes. You can also do the astroseismology. That gets you the most excellent measurements we can think of in terms of getting the size of the stars and the size of the planets. So basically, this is what we need to do. We need to look at 100,000 stars. We need to do that because if you pick a particular star and ask, is there a planet around it? If there is, your real question is the orbital plane lined up in your line of sight? If it's face on, you will never see the planets. It can have dozens of planets. You'll never see them. It has to be edge on. Then you see the transits. The probability of that happening is reasonably high for inner planets. 10% for the giants people often talk about. But for Earth, in a habitable zone, that's 0.5%. 0.5% means you can point out a bunch of nearby stars and ask, look at that photometrically. Does it have those stars have planets? God only knows. This method is not going to tell you that. But if you have 100,000 stars, and the percent's 0.5%, you ought to find 500 if most stars have planets. And if you find 0, there's not going to be a Star Trek. There's no place to go. So we're looking to find out, is that number somewhere between 0 and 500? The instrument shown here, it's a Schmidt telescope corrector, 1.4 primary mirror. Light comes in here, hits the primary. It's focused on the focal surface. It's not a focal plane. It's about a square foot of CCDs. This system basically is your CCD camera, the CCD camera that you might have at home to take pictures of your kids when they first walk. But our CCDs cost several $1 million. There's 95 million pixels, and they are very elegant CCDs. They allow us to find very low signals and a lot of noise. Fine guidance sensors, the system actually looks at the stars that we're watching and uses that to guide with. The guiding on this telescope is at least as good as that on the Hubble Space Telescope. It's that excellent. This is the focal plane. What you can see are the 42 detectors. They come in pairs. Each is covered with 2-inch squares of sapphire. The curvature is so extreme on the system because the field of view is so enormous. It's over 100 square degrees. Typical telescopes like Hubble Space Telescope look at a field of view like a grain of sand held at arm's length. Beautiful image, but a very tiny field of view. This system looks at something like 40,000 times larger in the area of the sky, but the images are fuzzier on purpose. We do not want the stars focused well, because otherwise we would saturate all the detectors. So these are our detectors, and that's in our telescope here. You can see the people here. The telescope is about the size of a VW bus and about a similar mass. There's our high-gain antenna. The spacecraft is actually just this ring around the instrument. And the high-gain antenna transmitters and the reaction wheels to hold it on pointed correctly are all in this ring. High-gain antenna means that once every month the spacecraft stops taking data, rotates around, points at the Earth, and dumps the data down in a stream over several hours, then rotates back. The color, the dispersion here is shown here. We really don't have filters other than we cut the ultraviolet out and we cut some of the infrared out. The ultraviolet is cut out simply because stars have spots, and those spots have an enormous variability in the ultraviolet. So we cut that out, and we just have a very broad spectral range here. But we have a detector that looks like this, a filter, a single one on a coating that basically sees to it our data comes from a very broad spectral range, but gets rid of the ultraviolet. The observations I'm going to talk about today were basically the ones done early on in the mission. It takes months to get the data back. It takes months to reduce the data so that we can actually talk about something that's not just noise. And so that's what we're going to be talking about today. Our operations began 12 May of 2009. We looked at 156,000 stars. And we also include some red giants because we do astrometry. The idea is if you do astrometry, you can tell how far away your stars are. If you know how far away your stars are, and you measure the temperature of the star, and you measure the flux of the star, you can tell the size of the star. The size of the star is important to the size of the planet. So we do that. We also look at some exoplanets, some eclipsing binaries. Eclipsing binaries are rather important to us. We found, in fact, several thousand. An eclipsing binary means the stars are orbiting in your plane of sight. That's why they eclipse. That's where you expect the planets to be. So again, that's an important aspect of what we're doing. So the first 43 days of observation I'll talk about, we found over 700 candidate planets, almost 1,000. In fact, we found 1,300 of which we have tossed out, so that these couldn't possibly be planets. 2,000 eclipsing binaries, thousands of variable stars are visible, and we'll look at some of those this morning. We knew when we launched there was a planet in one around one of the stars that had been found by the ground. The question is, when we saw it, what would it look like? And so this is a Jovian-sized planet orbiting a star in our field of view, known prior to our launch. Our data is shown here. If you looked at the data itself from the ground-based system, you really couldn't recognize the transit. It was buried in the noise, but again, by averaging down, by seeing many transits, they could find it, they could be sure. And so we've looked at it, and now, of course, our noise is 100 times lower, and the transit is just obvious by eye. You don't need any sophisticated programs to find it. You can see it immediately. But what you need to look at is that right there. That's the dip of a planet, or that's the dip whose size is the same.